We are going to start now lecture 5 of chapter 4, class 12th mathematics, determinants. In this lecture we will study about the inverse of a matrix using the determinants. So first of all we define the adjoint of a matrix. So suppose a matrix is given to us, the elements it has, it is A11, A12, A13, then A21, A22, A23, A31, A32, A33. This is the matrix A we are saying. Now corresponding to this matrix we have the cofactors corresponding to each of these terms. So cofactor corresponding to A11 we represented with A11, cofactor corresponding to this it is A12, cofactor corresponding to this it is A13. So if we write another matrix, we are talking about adjoint of A, we are writing a matrix whose elements are basically the cofactors of this matrix A11, A12, A13, A21, A22 and A23, A31, A32 and A33, and the transpose of this matrix. We are saying the transpose of this matrix, that is called the adjoint of the matrix A. So adjoint of matrix A has the elements, the cofactors of these terms, these elements, and the transpose of whole this matrix. It is called the adjoint of the matrix, and it is represented in this way. We can write in short form in this way, the adjoint of A. So if A2 cross 2 matrix is given to us, we are talking about this, it is A is equal to 2, 5, 1 and 3. Then the cofactors corresponding to each term, A11 that is equal to 3, then A12 that is equal to minus 1, because we will have signs over here, it is positive, negative and negative, or what we are saying, it is minus 1 raised to the power 1 plus 2 into 1, so answer comes out to be minus 1. Next A13 will be equal to A21, A13 is not there, it is A21 will be equal to minus 5 and A22 will be equal to 2. This is 2 over here. So when we are writing the adjoint of A, so we are writing these elements over here, it is 3, minus 1, minus 5 and 2, and the transpose of this matrix. So the answer for the adjoint we have, it is 3, minus 1, minus 5 and 2. So this is the adjoint of this matrix. Now next we have, if A is this 3 cross 3 matrix, we have to write the adjoint of A. So we are writing the cofactors over here, the cofactors corresponding to the terms. We are talking about the cofactor corresponding to this first term, it will be A11, that is equal to, how we write cofactor, we leave this row, we leave this column, what we are left with is, the 2, 1, 5, 3. Next, when we are writing the cofactor corresponding to A12, it means we are saying that we are leaving this first row and this second column. So the answer we obtain, that is equal to, it is minus sign over here because it is 1, 2. So it is minus 1 raised to the power 1 plus 2, it is negative sign over here. And the elements we are left with is 0, 1, minus 4 and 3. So the answer we obtain, that is equal to minus 4. So likewise we have to write all the cofactors. This is A13 is 8, A21 is 26, A22 is 19, A23 is 3, A31 is minus 10, A32 is minus 1 and A33 is 2. So these are the elements of the, these are the cofactors corresponding to these elements. So when we have to write the adjoint of A, we are writing A11, we have seen it is equal to 1, then it is minus 4, then it is 8, 26, 19 and 3, minus 10, minus 1, 2, and transpose of this matrix. And when we do the transpose of this matrix, we obtain the matrix in the form 1, minus 4, 8, 26, 19, 3, then minus 10, minus 1 and 2. So this is the adjoint of the given matrix A. Now the next theorem we have is if A is a square matrix of order n, A is any square matrix of order n, then we have to prove that A into adjoint A is equal to adjoint A into A, that is equal to determinant of A into I. So to prove this result, we are writing this matrix A is there, its elements we are writing it in this form, that it is A11, A12, A1n, so on up to AN1, AN2, so on up to AN. It is a n cross n matrix, and the adjoint of this matrix corresponding to A11 we will have the term A11 over here, corresponding to A1n we will have capital A1n over here. These are the cofactors, and we have already done the transpose. These are the elements we are talking about. This corresponding to these terms we have done the transpose over here, and we are obtaining the elements in this form. So this is the adjoint of A. So if we multiply A with the adjoint of A, so the first term, if we are talking about any general term over here, I am talking about this AI1, say AI2, AIN, it will be multiplied with the terms over here. Say I am talking about some kth row is there, and the elements in this kth row, they are AK1 and it is AKN. So what we will get is that AI1, that will be multiplied with AK1, then it is plus, then AI2 will be multiplied with AK2, so on up to AIN, small, it is not this one, it is the term we are talking about AIN, that will be multiplied with AKN. And the answer we obtain, we know that when we are talking about, we have already seen the result that when element is multiplied by its own cofactor and we add them, the answer we obtain, that is equal to determinant of that matrix. So we are writing when I is equal to k, so we are talking about AI1 AI1 plus AI2 AI2, so on up to plus AIN AIN. When element and its own cofactor, these are multiplied, the answer we obtain, that is equal to determinant of A. Otherwise the answer is equal to 0 when I is not equal to k. So this thing is mentioned over here, that we have when these terms, these are multiplied, then it is equal to determinant of A when I is equal to k, and it is 0 when I is not equal to k. So what we are writing over here in general, that when we are talking about A into adjoint A, these are the diagonal terms we are talking about. When I is equal to k means we are talking about this diagonal. So on the diagonal we are getting determinant of A, and all other entries, they are equal to 0. Now an important thing to note over here is that this is a matrix. This is a matrix, this is not determinant, this is a matrix. So we can write this determinant of A common from all these terms, it will be multiplied with all these terms. So we are left with this 1 1 1 over here. These are just the numbers. When we are talking about determinant of A, it is just a number, and we know that when we multiply a matrix with any number Aij, say I am writing, so each element is multiplied with that number. So we are writing determinant of A, which is a number we have taken common, and this is now we have identity matrix. So what we obtain from this is, the final result we have obtained is that A into adjoint A is equal to determinant of A into I, and similarly we can prove that adjoint A into A, that is equal to determinant of A into I. So in this next question, we are verifying this result with an example. We have already seen the proof, and now we are verifying this result with an example. So we are writing if A is equal to, we are talking about this matrix over here, it is 3 1 7 5. We have to verify that A is equal to adjoint A into adjoint A, that is equal to adjoint A into A, that is equal to I into A. So first thing we are going to do over here is we are calculating the determinant of A. So determinant of A, we have it is equal to, we have calculated its value is equal to 8. You know how to calculate the determinant of a 2 cross 2 matrix. So we obtain the answer is 8. Now next we have to calculate the adjoint of A. To calculate adjoint of A, we have calculated the cofactors. Cofactor corresponding to 3, it is 5. Cofactor corresponding to 1, it is -7. Corresponding to 7, it is -1, and corresponding to 5, it is 3. So the adjoint of A we have obtained in this term. So it is important, I am again mentioning over here that when we are writing the adjoint of A, we are writing it is 5 -7 -1 3, and it is transpose over here. So we are getting the answer in this form. This is the adjoint of A. Next we have calculated A into adjoint A. We have calculated adjoint A into A. We have two matrices. This is adjoint A. This is the matrix A given to us. We have multiplied both these matrices. You know how we multiply the matrices. We have already seen. So the answer we obtain in this case, it is 8 times I. This is equal to 8 means determinant of A into I, and this value is equal to determinant of A into I. So we are saying that this result is verified for this particular case. This is just the verification we are talking about. Proof we have already seen on our previous slide. Next is the definition of singular and non-singular matrices. So we are saying a square matrix. Important thing over here is we are talking about the square matrix. So a square matrix is said to be singular if determinant of A is equal to 0, and non-singular if determinant of A is not equal to 0. So these examples are given over here. We are talking about this matrix A is given. Determinant of this matrix comes out to be 0. It means it is a singular matrix. This second B matrix is given. Determinant of this B matrix is -2. It is non-zero. So we are saying this is a non-singular matrix. So next definition we have, it is invertible matrix. So we are saying a non-zero square matrix A. Non-zero, when we are saying, it means we are talking about that the entries of matrix, they are not 0. Order of the matrix, it is n, and it is said to be invertible if there exists a square matrix B of order n such that A B is equal to B, A is equal to I. This is just like the inverse functions we have already studied. Over there we were saying FOG is equal to GOF, that is equal to the identity map. Similarly, now here we are saying A into B is equal to B into A is equal to I. Then we can write that A inverse is equal to B, that is B is the inverse of A, or we are saying A is the inverse of B. So for any matrix A, if we can find another matrix B for which AB is equal to B is equal to I, then we say that the matrix A is invertible matrix. So invertible means we can find the inverse of that particular matrix. Next is an invertible matrix possesses a unique inverse. We have to prove this thing. So suppose we are saying that there is an invertible matrix A of order n. It is an n cross n matrix. So we have already seen that it should be a square matrix. So we are considering that its order is n. And suppose we are saying that it has two inverse. Its inverse is B, its inverse is C. If B is inverse, it means A B is equal to B, A is equal to I. If C is the inverse, then we have A C is equal to C, A is equal to I. Now suppose we are starting with this equation. We are writing A into C is equal to I, and we multiply both sides of this equation with the matrix B, because the order of all these matrices, these all matrices, these are of order n cross n. So multiplication is possible over here. Now look at this term over here. We can write it is B A into C is equal to B into I. And what is B into A? B into A is identity matrix. So this thing implies us that I into C is equal to B into I, and this thing implies us C is equal to B. It means how we have started the proof. We are saying suppose there are two inverses B and C. We are saying if there are two inverses, then they must be equal. It means that the inverse is unique. An invertible matrix has always a unique inverse. Next is a square matrix A is invertible if and only if it is non-singular. Non-singular we know, non-singular means determinant of A is not equal to 0. So we are saying if determinant of A is not equal to 0, then the matrix is invertible. That is, we can find another matrix B such that A, B is equal to B, A is equal to I. And if this condition holds, then it means that the determinant of A is not equal to 0. So we have to prove this. It is if and only if condition over here. So we have to prove this in two parts. One is, first part, we are considering that A is invertible. In the first part we are saying we are considering A is invertible. It means we are saying there exists a matrix B. If order of A is n cross n, B will be n cross n, such that A, B is equal to B, A is equal to I. Now look at this condition. We are saying A, B is equal to I. It means determinant of A, B is equal to determinant of I. And determinant of A, B means determinant of A into determinant of B should be equal to 1, because determinant of identity matrix is 1. So what this thing means? So this thing implies us that determinant of A cannot be equal to 0, because this determinant of A and determinant of B, both these are just the numbers, and we know that if product of two numbers is equal to 1, then none of them can be equal to 0. So what we see is that determinant of A cannot be equal to 0. This shows that A is non-singular. Now we prove the converse part. Suppose we are saying that the matrix A is non-singular. We are saying suppose matrix A is non-singular means determinant of A is not equal to 0. Then from our previous theorem we know that A into adjoint A, that is equal to adjoint A into A, that is equal to determinant of A into I. Determinant of A is not equal to 0. So what this thing implies is that A into 1 over determinant of A into adjoint A, that is equal to I, that is equal to 1 over determinant of A into adjoint A into A. Now look at this term over here. We can write this term as B. We are saying we are writing this term as B. B is equal to 1 over determinant of A into adjoint A. And if we are writing it in this form, then what we are getting? A, B is equal to B, A is equal to I. And this thing proves that A is invertible matrix, and the inverse of A, it is given by the formula 1 over determinant of A into adjoint A. So we have obtained a formula to find the inverse of a matrix, that is B is equal to 1 over determinant of A into adjoint A. So we have proved this theorem and we have obtained the formula to calculate the inverse of a matrix. So this formula we have already seen. We are saying that if A is a square matrix, determinant of A is not equal to 0, then A inverse is equal to 1 over determinant of A into adjoint A. Now we have to, this matrix is given to us, we have to calculate the inverse. So one method we have already studied in our previous chapter, which was using the elementary operations. Now this is using the adjoint. We are going to find the inverse using the adjoint. So we are writing A is equal to 2 minus 3 minus 4, 7. So first thing we are calculating, it is determinant of A, and the answer we obtain, it is 14 minus 12 is equal to 2, and clearly this is not equal to 0. So we are saying that this matrix, it is invertible, that is A inverse exists. Now we have to calculate adjoint of A. Adjoint of A, we have to write the cofactors. Cofactor corresponding to these terms, they are 7 4, 3, 2, and we have to take the transpose over here. So the answer we have, it is 7, 3, 4 and 2. Now the formula for A inverse we have, that is equal to 1 over determinant of A into adjoint A. So it is equal to 1 by 2 into 7, 3, 4, 2. So we can write the answer is 7 by 2, 3 by 2, 2 and 1. So this is the inverse of the given matrix. I am again explaining the steps. First step we have is, we are writing this element matrix A. We have calculated determinant of A. If it is non-zero, we are saying A inverse exists. If this answer comes out to be 0, then we cannot find the inverse. Next step we are doing is, we are calculating the adjoint of A. This transpose is very important over here. We have written the adjoint of A. Then A inverse is equal to 1 over determinant of A into adjoint A, and we obtain this answer. So this is one of the methods to calculate the inverse of a matrix. Next, we are given a 3 cross 3 matrix and we have to find the inverse of this matrix. Again, what are the steps? We are writing, suppose this matrix is equal to, this matrix we are saying this is equal to A. We have calculated, this is step 1. We have calculated determinant of A. Now determinant of A, when we are calculating, we have applied the row elementary operations also over here, and we obtain that the determinant comes out to be minus 16 and it is not equal to 0. So we are saying that A inverse exists. If this answer comes out to be 0, we cannot find the inverse. We will leave the question up to this and we will write that A inverse does not exist, but in this case we will have the inverse. And to find the inverse, next step we have to do is, we have to write the cofactors of elements of determinant of A. So this is how we are calculating the cofactors corresponding to this first term. We have the value minus 8, and similarly we can calculate the values corresponding to the second term. We have the value corresponding to this second term, we have the value 0. Corresponding to this third term, it is minus 8. Now an important point to note over here, first is that whenever you are calculating the cofactors, you are not going to use this matrix. You have to use the original matrix. It means, I am saying, after applying some row or column operation, you have obtained some matrix. We are saying determinant of both these matrices are equal. It doesn't mean that their cofactors are also equal. So this thing you must keep in mind, that whenever you are calculating the cofactors, you are calculating the cofactors of this matrix. You are calculating the cofactor of this matrix. This is a common mistake that students commit. And the second thing is, whenever you are writing the cofactors, you must keep in mind the signs that we have to assign over here: positive, negative, positive, negative, positive, negative, positive, negative, and positive. These signs are very important over here, that you must assign these signs over here. These are some common mistakes that students commit while doing these calculations, that they do not put signs over here, they just write the values. And this is the second thing that you must keep in mind, that you must put the signs. And third is, when you are writing the adjoint, you must do the transpose. So we are saying these are the cofactors. So the adjoint will be minus 8, 0, minus 8. Then it is minus 16, minus 4, minus 8, minus 12, minus 4, 4, and the transpose of this matrix. So we are obtaining the adjoint of this matrix in this form, and the final answer we are getting, we are writing it is 1 over determinant of A into adjoint A. This is 1 over determinant of A into adjoint A, and this is the final answer. We obtain the inverse of this matrix. So I am again repeating the steps. First of all, we are calculating A, determinant of A. it is non-zero, so we are writing its inverse exists. Next step, we are calculating the cofactors corresponding to the elements. We must use the original matrix, we must put the signs, and when we are writing the adjoint of A, we must do the transpose. So after this, we are going to multiply 1 over determinant of A to the adjoint A, and this is the answer we are obtaining for the A inverse. Next, we have the cancellation law over here. So we are saying let A, B, C, these are the three square matrices we are talking about of order n, such that AB is equal to AC, and it is given that A is a non-singular matrix. It is given that A is non-singular matrix. Then we have B is equal to C. So we are writing it in this form. We are saying suppose AB is equal to AC, this is given to us. Next thing that is given to us is that A is non-singular. If A is non-singular, it means A inverse exists. That is, we are saying determinant of A is non-zero, A inverse exists. So if we multiply both sides of this equation with A inverse, we are writing A inverse AB, that is equal to A inverse AC. We can write it is equal to A inverse A into B, that is equal to A inverse A into C. So this is basically the identity matrix. A inverse into A is I, A inverse A into I into B is B, and this is C. So what we obtain is that B is equal to C. But if A inverse does not exist, it means determinant of A is equal to I, then A inverse does not exist, then we cannot multiply it over here. So in this case, when A determinant of A is equal to 0, then this thing, it is not necessary that B is equal to C. So an example is given over here. We are saying suppose the matrix A is 1 2 3 6, matrix B is this 2 0 0 0, and matrix C is this matrix. Now in this case, determinant of A is equal to 0, and if we calculate the value of A into B, and if we calculate the value of A into C, both are equal. We are saying in this case, if we calculate AB, then that is equal to AC, but B is not equal to C, and this is because A is not invertible. That is, determinant of A is equal to 0. So B will be equal to C. For this condition, this is the condition that we have. We are saying that this result, that if A is non-singular, we are saying if determinant of A is not equal to 0, then B will be always equal to C, and if the determinant is equal to 0, then it is not necessary that B is equal to C. So cancellation law only holds when A is non-singular. Next is reversal law. So we are saying if A and B, these are two invertible square matrices of same order, then A into B is also invertible, and AB inverse, that is equal to B inverse into A inverse. So what is given to us is that A and B both are invertible matrices. It means determinant of A is not equal to 0. It means determinant of B is not equal to 0. Now if we have to check whether AB is invertible, we are saying determinant of AB, that is equal to determinant of A into determinant of B. Both these values are non-zero, so it means this value cannot be equal to 0, and this thing implies us that A into B is also invertible. Now next thing we have to prove is that AB inverse is equal to this value. So if we write AB into B inverse A inverse, we have to prove that inverse of AB is equal to B inverse A inverse. So we have multiplied A, B with this term. What we get is, it is A into B inverse into A inverse. This is equal to A I into A inverse. This is equal to A inverse, and that is equal to I. Similarly, if we are writing B inverse A inverse into AB, answer we are getting it is B inverse into A inverse A into B. This is equal to B inverse I into B. This is equal to B inverse into B, and this is equal to I. So what we obtain from this is that AB inverse, that is equal to B inverse into A inverse. We have proved this thing. This is one matrix. We are saying this is just like C into D. We are saying that is equal to D into C, that is equal to I. So what we get is that D is the inverse of C. So we are writing that AB inverse is equal to B inverse into A inverse. Next is, if A is an invertible square matrix, then we have to prove that A transpose is also invertible, and A transpose inverse is equal to A inverse transpose. So we are, if a matrix A is given, we have to find the A transpose inverse. So we can calculate the A inverse and do its transpose. So first, to prove that A inverse is invertible, we are saying it is given that A is invertible. It is given that A is invertible. It means determinant of A is not equal to 0. If determinant of A is not equal to 0, then this thing implies us that the determinant of A dash is not equal to 0. Transpose of A is not 0, and this thing means that A in transpose of A is invertible. Now, if we have to calculate the inverse, we are talking about A into A inverse, that is equal to A inverse into A, that is equal to I, because it is given that A is invertible. Now, if we do the transpose of whole of this equation, we will obtain it is A into A inverse transpose, that is equal to A inverse into A transpose, that is equal to I. From our previous result, we know that A inverse transpose into A transpose, that is equal to A transpose into A inverse transpose, that is equal to I. Now what this thing means? Look at this term over here. What this thing means? That A transpose inverse, that is equal to A inverse and whole transpose, and this is what we have to prove. Next is, if A is an invertible symmetric, then prove that A inverse is also symmetric. Now first thing that is given is A is A invertible. It means determinant of A is not equal to 0 and A inverse exists. And further it is given that it is symmetric. It is symmetric means A is equal to A transpose. We have to prove that A inverse is also symmetric. So to prove A inverse is symmetric, we are writing A inverse transpose. And we know that this is equal to, from our previous result, from this result we are talking about, we know that this value is equal to A transpose inverse. Now it is given that it is symmetric. We are saying it is symmetric. It means A transpose is equal to A. So we are writing it is equal to A inverse. So what we are getting over here is that A inverse transpose is equal to A inverse. It means A inverse is also symmetric. Next is, if A and B are non-singular matrices of same order, then prove that adjoint of AB, that is equal to adjoint of B into adjoint of A. So again, it is given that A and B are non-singular matrices. It means determinant of A is not equal to 0, determinant of B is not equal to 0. Their order is same. Suppose their order is n. So what we get is that A B determinant is not equal to 0. We have already seen. So, and we know that A B inverse will exist. This thing we have already seen. Now, if we are writing A inverse, we have that is equal to 1 over determinant of A into adjoint A. If we are writing B inverse, it is 1 over determinant of B into adjoint B. These formulas we have already seen. How we have calculated these formulas, we know. Now, if we are writing A B inverse, that will be equal to adjoint of AB divided by determinant of AB. Now, from this result we can write adjoint of AB, that is equal to determinant of AB into AB inverse. We have shifted this term on this side. So what we get, we can write this is equal to determinant of A, determinant of B into B inverse into A inverse. So we are writing this is equal to determinant of A into determinant of B, and this value is 1 over determinant of B into adjoint B, 1 over determinant of A into adjoint A, and the answer we get, this B and A gets cancelled and we are left with this adjoint B into adjoint A. So we have proved the result that adjoint of AB, that is equal to adjoint of B into adjoint of A, and this is what we have to prove. This is what we have to prove, that adjoint of AB is equal to adjoint of B into adjoint of A. Next is, for any square matrix A, prove that adjoint of A transpose, that is equal to adjoint of A transpose. This is whole adjoint of A whole transpose, and in this second case we are talking about, it is A transpose adjoint. So for to prove this result, we are saying, suppose A is a square matrix of order n, then adjoint A transpose and A transpose adjoint both are square matrices of order n. This thing is clear to us. Then next thing we have is that ijth element of adjoint of A transpose, we are talking about, it is ijth element over here, and that will be jith element of, this is transpose over here, and we are talking about adjoint of A, and that is equal to cofactor of ijth element of A. It is A over here, we are talking about A transpose, this is ijth element over here, we are talking about jith element over here, and that is equal to jith element of adjoint of A transpose, and hence we obtain this result. Next is, if A is a non-singular square matrix of order n, then we have to prove that adjoint of A determinant, that is equal to A raised to the power n minus 1, that is determinant of A raised to the power n minus 1. So we know that A into adjoint A, that is equal to determinant of A into I. Now if we take the determinant on both these sides, we obtain that determinant of A into determinant of adjoint A, that is equal to determinant of A raised to the power n into determinant of I. What I want, determinant of I. Now why this A raised to the power n is there? We are saying, when we are talking about this term, look at this term, it is basically determinant of A, determinant of A, determinant of A, so on up to determinant of A, and it is a n cross n matrix. All these entries, these are 0, all other entries, these are 0. So when we calculate the determinant of this matrix, how many A's are there? Determinant of A are there are total n elements. So when we calculate the determinant over here, we get it is determinant of A raised to the power n. So from this result we can write it is determinant of adjoint A is equal to determinant of A raised to the power n minus 1. We are dividing this term on this side and we are getting the answer in this form, that adjoint of A, that is equal to determinant of adjoint A, that is equal to determinant of A raised to the power n minus 1. Next is, if A is a non-singular square matrix of order n, then we have to prove that adjoint of adjoint A, that is equal to A raised to the power n minus 2 into A. So suppose we are saying there is a non-singular matrix B and we are talking about the value B into adjoint B. We know that the answer for this, that is equal to determinant of B into I. It is determinant of B into I. So if we take B is equal to, we are taking B is equal to adjoint of A, the answer we will get it is adjoint A into adjoint of A, that is equal to determinant of adjoint A into I. This is determinant of adjoint A into I, and we know that the value of determinant of adjoint A, we have seen it is determinant of A raised to the power n minus 1 into I, and over here we have the value, it is adjoint A into adjoint of A. Now if we multiply this whole equation with A, we are multiplying both sides of this equation with A, we have the term A into adjoint A over here, and A into adjoint A, we know it is determinant of A into In into adjoint of A, and that is equal to this value, it will become determinant of A raised to the power n minus 1 into A. Now when In is multiplied over here, this will be remain as it is and it will be adjoint of A, that is equal to determinant of A raised to the power n minus 2. It is determinant of A over here, we shift it on this side, we obtain it is power is n minus 2 into A, and this is what we have to prove. We are saying adjoint of adjoint A is equal to determinant of A raised to the power n minus 2 into A. Next is, if A is equal to, these matrices are given to us, A is equal to this matrix, B is equal to this matrix, we have to verify that AB inverse is equal to B inverse into A inverse. So first of all, we are talking about this matrix A and we calculate the determinant of A and it comes out to be 1, and clearly it is not equal to 0, so it means A inverse exists. So if we calculate A inverse, that will be equal to 1 over determinant of A into adjoint A. So that is equal to, if we write the adjoint A over here, the elements will be 5 minus 2 minus 7 and 3. This is 5, then minus 2, then minus 7 and 3, because we have to take the transpose, so we get the answer in this way. Similarly, if we calculate determinant of B, the answer is minus 2, again it is not equal to 0, and adjoint of B is 9 minus 7 minus 8 and 6. So B inverse, when we calculate, it is 1 over determinant of B into adjoint B, so we get this answer. Next thing we have to calculate is A into B, determinant of A into B. So when we calculate determinant of A into B, we know that it is equal to determinant of A into determinant of B, so that comes out to be minus 2 and it is not equal to 0. So we are saying that determinant of AB is non-zero, it means it is invertible. So to write the adjoint of AB, we are using the formula that is equal to adjoint of B into adjoint of A. We know the value of adjoint A, we know the value of adjoint B. So when we multiply both these, we obtain the answer, it is 94 minus 39 minus 82 and 34. 4. So this is one of the method to find this. Otherwise, what you have to do, you have to calculate A into B, and then you have to calculate adjoint of AB. So it is up to you that how you want to calculate adjoint of AB. So when we multiply these values, we obtain the answer in this form, that this is the value of adjoint of A into B. Now we have to verify that A B inverse, that is equal to B inverse into A inverse. So we calculate the value of B inverse into A inverse. The value of B inverse we have, this is the value of B inverse, this is the value of A inverse. We multiply both these and we obtain, when we multiply both these, we obtain this value is equal to minus 1 by 2, 94 minus 39 minus 82 and 34. Determinant of mod of AB is minus 1 by 2. So what we get is this is equal to 1 by determinant of AB into adjoint of AB, and this is what we have to prove. This is what we are being asked to prove, that AB inverse is equal to B inverse into A inverse. Next is, if the matrix A is equal to this is a 3 cross 3 matrix, and it satisfies the equation A square minus 4A minus 5I is equal to 0, we have to calculate the value of A inverse. So if we are saying that the matrix A satisfies this equation, we are calculating the value of A inverse. So we suppose that A inverse exists. We first suppose that A inverse exists, that is this matrix, we are supposing it is invertible. So if we multiply this equation, talking about this equation, if we multiply this equation with A inverse, we get it is A inverse into A square minus 4A inverse into A minus 5A inverse into I, that is equal to O into A inverse. O is the 0 matrix we are talking about, it is 0 matrix, and we know that if we multiply it with A, the answer we obtain it is 0 matrix again. Now A inverse into A square means we are talking about A inverse into A minus 4 times A inverse into A minus 5 times A inverse is equal to 0. Now look at this term over here, it is A inverse into A, this is A inverse into A, and we know that the value of A inverse into A, it is I, this value is I. So we get A minus 4I minus 5A inverse is equal to 0. So this gives us A inverse is equal to 1 by 5 into A minus 4 times I. So if we look at these values over here, this is the value of A we have, and 4 times I means we are talking about it is 4 times I is this. So this determinant over here, this will be 400 040 004. So when we subtract these two values, we obtain the answer in this form, and that is equal to A inverse. This answer is equal to A inverse. So this is the required value. So we are saying if when the A inverse exists, we are having A inverse is equal to this value. Now suppose we are saying in this case that A inverse does not exist. We have some equation in the form, I am talking about some matrix is there, say some matrix B is there, and it satisfies B square minus B is equal to 0, and we suppose that, suppose we are saying that, suppose B inverse exists, we are writing suppose B inverse exists, then we are multiplying it with B inverse, we are getting B inverse into B square minus B inverse into B is equal to 0. So this implies us, this term it is identity matrix, and this term we are getting it is equal to B. So what we will get, B is equal to I. It means B is the only matrix, I is the only matrix which satisfies this, and the B inverse will be then the identity matrix. This is the only invertible matrix. Identity matrix is the only invertible matrix which satisfies this condition, otherwise no other matrix can satisfy this condition. So whenever we are supposing solving these kind of questions, so we can suppose that A inverse exists, otherwise we have to check whether its determinant is non-zero or not. Apart from this, in your higher classes you will study the Cayley-Hamilton theorem, and from there, by looking at this equation, we can tell that this A is invertible. But this is, we are not going to discuss those cases over here, that are not the part of your syllabus. So you can suppose over here that A inverse exists. Next is find a matrix X such that X into this is equal to, we are given X into this matrix 2, 3, 2, 1 minus 1 is equal to 4, 1, 2, 3. So we are writing, so this is in the form X into some matrix A is equal to B. Now if we look at this matrix, we are writing A is equal to matrix 3, 2, 1 minus 1. Determinant of A will be equal to minus 3 minus 2 is equal to minus 5, which is not equal to 0. It means A is invertible. It means A inverse exists. So if we multiply this equation, we are talking about X into A is equal to B. We are multiplying this equation with A inverse. We get X into A inverse is equal to B into A inverse. Now A into A inverse is I. So what we get is X is equal to B into A inverse. Now the value of A inverse we will have, that is equal to 1 by minus 5 into adjoint of A transpose, and the value we will have it is minus 1, minus 1, minus 2 and 3. This is value of A inverse. This is adjoint is the cofactors we have written, and we have taken the transpose over here. So this is value of A inverse that we have. Now we have to calculate B into A inverse. This is the value of A inverse. We have the matrix B, that is 4, 1, 2, 3. So when we multiply these two matrices, we obtain the value of X as 1, 1, 1 and minus 1. We have shown the multiplication over here, that we are multiplying these two matrices. We obtain this answer. It is minus 1 by 5 over here. So we are obtaining the final answer in this form, and this is the required value of X. This is the required value for X. Next is find the matrix A satisfying this equation. Now this matrix we can write it in the form that B A C is equal to I, where B is equal to matrix 2, 1, 3, 2, C is equal to matrix minus 3, 2, 5 and minus 3. Now determinant of B we have, we are talking about determinant of B we have, that is equal to 1, and the determinant of C we have, that is equal to minus 1. Both of these are non-zero. It means B inverse and C inverse will exist. So if we multiply this equation from the, we are having the equation B A C is equal to I. We are multiplying this equation on this side by B inverse and on this side by C inverse. We are operating from the left B inverse, we are operating from the right C inverse. So look at this term, B inverse into B will be I, C inverse into C will be I. So what we are left with over here is that A is equal to B inverse I into C inverse, that will be just C inverse. So we are interested in calculating the value of B into C inverse. So we have to calculate B inverse, we have to calculate C inverse, and we have to multiply these values. So the value of B inverse, it is 1 by determinant of B into adjoint B. The value of C inverse, it is 1 by determinant of C into adjoint C. We obtain these two values. These are the values of, this is the value of B inverse, this is the value of C inverse. We have multiplied both these values. We have multiplied both these values and we obtain the final answer in this form, that A is equal to B inverse into C inverse. So this is our final answer. Next question we have is, if this matrix A is given, we have to verify that adjoint of A inverse, that is equal to A inverse adjoint. So to calculate the value of A inverse, and we are talking about the inverse over here. So first thing we are going to do, we are going to calculate the value of determinant of A, and it comes out to be minus 13, which is not equal to 0. So we can say that A inverse exists. So now we are calculating the adjoint of A. To calculate the adjoint of A means, talking about adjoint of A, and we are calculating this value. The first term we will have over here, it is corresponding to this matrix. We are leaving this row, we are leaving this column. The element we will have over here, it is, we write this over here, that will be 3, determinant of 3 1 1 5. Next will be with the negative sign. We will leave this row, we will leave this column, and the elements we will have over here, they will be minus 2 1 1 and 5. Similarly, we will have third term. Likewise, we will write the cofactor of all these terms, and then we will do the transpose over here. On solving this, we will obtain the answer in this form, that the adjoint of A, that is equal to this value. So to calculate the value of determinant of A, we have calculated it over here, it is minus 13. So A inverse is equal to 1 over determinant of A into adjoint A, and the answer comes out to be in this form. So you can try these calculations and you will obtain the answer in this form. Now what we have to verify is, we are going to verify that adjoint A inverse, that is equal to adjoint A inverse adjoint. So basically, if we are able to prove that adjoint A into adjoint A inverse is equal to I, so both these conditions, these are equivalent. We are writing that A inverse is equal to B, or we prove that A into B is equal to I. Both these conditions, these are equivalent, or B into A is equal to I. These conditions, these are equivalent. So in place of calculating the adjoint of A inverse, we are calculating the value of adjoint of A into adjoint of A inverse. Now we have the value of adjoint of A inverse. We have calculated the value of A inverse over here. From this matrix, we are going to calculate the value of adjoint of A inverse. Now if we multiply both these values, this is adjoint of A inverse, and this is the value of adjoint of A. If we multiply both these values, we will obtain, on multiplying both these values, we will obtain that the answer is the identity matrix. So what we have obtained? We have obtained that adjoint A into adjoint A inverse is equal to I, and this is equivalent to the statement that adjoint A whole inverse, that is equal to adjoint A inverse, and this is what we have to prove. So we are saying that adjoint A into adjoint A inverse is equal to I. So adjoint, similarly we can prove that adjoint A inverse into adjoint A is I. So by combining both these results, we are obtaining the required result that adjoint A inverse is equal to adjoint of A inverse. So we have already proved this result, and this is just the verification part for a particular 3 cross 3 matrix. So we have verified this result. Next is this A is given. A is the given matrix. It is having element 2 3 1 5. We have to verify that A transpose is equal to A transpose inverse is equal to A inverse of transpose. So first of all, we are calculating the determinant of A, and determinant of A comes out to be 7, so it is not equal to 0. So this thing implies us that A inverse exists. So to calculate A inverse, we are writing the adjoint of A, that is equal to 5 minus 1 minus 3 2 transpose, that is equal to 5 minus 3 minus 1 2. So A inverse is equal to 1 over determinant of A into adjoint of A. So this is the value of A inverse. Now if we take the transpose of A inverse, the answer we obtain it is 1 by 7 into 5 minus 3 minus 1 2. So this is the value we are talking over here. Next we are talking about the A transpose inverse. So when we are writing A transpose, the value we have it is 2 3 1 5. Determinant of A transpose will be equal to again 7, because we know that determinant of A and determinant of A transpose, they are equal. Now for this matrix we are writing adjoint of A transpose. The value we have it is 5 minus 1 minus 3 2. When we multiply this term with 1 over determinant of A transpose, we get it is 1 by 7 into this. So we can clearly see that both these values we are talking about, they are equal. Both these values, these are equal, and this is what we have to prove for this particular matrix. For the matrix A, we have proved that A transpose inverse is equal to A inverse transpose. Next is, if A is equal to this matrix 1, tan x, minus tan x and 1, we have to prove that A transpose into A inverse is equal to this value. So first of all, we are calculating the determinant of A. So that will be equal to 1 plus tan square x, that comes out to be secant square x, and it is not equal to 0. Next thing we have to calculate is, we have to calculate A inverse. So we are calculating adjoint of A. So the value we will have, that is equal to 1 minus tan x and 1 and its transpose, and it comes out to be 1 minus tan x and 1. Next thing we are calculating is A inverse. So it is 1 over secant square x into 1 minus tan x and 1. Next we have to calculate is, next thing that we have to calculate it is A transpose into A inverse. So the value we obtain, that is equal to 1 minus tan x and 1, and we are multiplying it with 1 over secant square x, 1 minus tan x and 1. So when we are solving this value, we have multiplied this value we are talking about, it is cos square x, 1 over secant square x will become, this 1 over secant square x will become cos square x. When we multiply these terms, this matrix will come in this form, that it is cos square x minus tan x cos square x, tan x cos square x and cos square x. And when we multiply these values, we are talking about these values over here, the answer we obtain, that is equal to cos 2x minus sin 2x and cos 2x, which is the required determinant. So you can calculate these values at your own. You can try to calculate these values and obtain this matrix.